So we said on Tuesday that Cauchy's convergence criterion allowed us to remove any reference to the particular limit L that a sequence approaches, and instead only reference the elements of the sequence. This is especially useful when looking at a series. All right, so let's suppose that we have a series Sn. Cauchy's convergence criterion states that this series converges if and only if given any epsilon greater than 0, there exists a capital N. So remember what that means. It means there's a far enough down the list, down the sequence, that you can go. Such that has a bunch of different ways, a bunch of different shorthands for it. A colon is such that, also big long bar is such that. And there's a couple of other ones that we can use to indicate such that. So there exists far enough down the sequence such that the absolute value of Sm minus Sn is less than epsilon whenever M and N are both far enough down the sequence. Now, if my sequence is actually a sequence of partial sums of another sequence, right? Then what this will be written as is the absolute value of the sum from k equals. All right, so now I'm looking at the difference between the sequence elements at two values that are larger than capital N. All right, so I'm going to write that as the sum from k equals capital N plus 1 to capital N plus P of AK, like that. So this would be, these values would be lowercase n is capital N plus 1, and M is capital N plus P. So this would be the difference, Sn plus P minus S, I guess I misspoke, minus Sn, not N plus 1. All right, this would be less than epsilon. Okay? So a series converges whenever we, given any epsilon greater than 0, we can find a capital N such that the sum of any number of terms, this P, can be any natural number. All right, the sum of any number of terms past this given term in absolute value must always be less than epsilon. And this is what we're going to use in order to establish the convergence tests that you studied in single variable calculus.